Okay, we're going to start this video reviewing the coordinate system. So the coordinate system uses two axes, a vertical, which is the y-axis, um, and the horizontal or the x-axis. So this is the x-axis, and this is the y. This one up here is the y-axis. And the way we represent points is by writing the distance from the y-axis to the point, which is interesting because it is the x number. So it is confusing a little bit. Okay, so if you have this point here, how far is it from the y-axis? And it is 3 units to the right, based on this, 1, 2, 3. So 3 units to the right, and that's the number we put here. So that is the distance from the y-axis across horizontally. The distance from the x-axis is 2. So we go in the x direction first, and then in the y direction. At the same time, that is the distance from the y-axis, and then the distance from the x-axis. That is a little bit confusing. So practice how to plot numbers on the coordinate system. So this is the Cartesian coordinate system. Practice how to plot points on the Cartesian coordinate system. Don't neglect to do that. It is very easy to miss and to forget and to start the numbers the other way around, perhaps. The two axes that form the coordinate system intersect at 0. So the x-axis starts 0 here and then goes positively on the right direction, on the direction to the right. And then the y-axis, the 0 of it is there where they intersect, and it goes positively on the up direction. So up is positive, to the right is positive, to the left is negative, down is negative. That is a convention, by the way. In some engineering problems, we have to change those directions to make the numbers work a little better. But if nobody changes them, if nobody tells you there's a change, we always assume I guess the default is that on the right we have the positive numbers, up we have positive numbers, on the left negative numbers, down negative numbers. Become very familiar with this setup. It is very easy to underestimate how important it is to become familiar with it. Because once you obtain solutions, if you are familiar with the coordinate system, then you may realize that your solution might not make sense for a particular problem. And that way you can detect perhaps mistakes. The coordinate system is divided into 4 quadrants, 1, 2, 3, and 4. 4 quadrants. So each one of these regions that's the coordinate axis split the whole plane into are called quadrants. So the quadrant here is labeled as quadrant number 1 with Roman numbers typically, but not necessarily. And then this is quadrant 2, the region over here on the upper left of the plane. On the lower left region, we label that as quadrant 3, and then the lower right region is labeled as quadrant 4. So we got 1, 2, 3, and 4. The axes themselves, I don't think belong to any region because they're in between regions. So the region is the stuff that is inside. The points on the left in quadrant 2 have coordinates where the first entry, the first number is negative and the second number is positive. So we have negative, positive. Here we have negative, negative numbers. Oh, not necessarily -1. I just meant to put a negative as a symbol indicating that we have negative, negative. And then over here we have positive, negative. And this number or this point is positive, positive. So we can recognize where a point belongs to quadrant 1, 2, 3, or 4, simply based on what kind of numbers we have. Now, if we have a point right on the center on the line, then that doesn't belong to any quadrant. It's between two quadrants. And then this point right in the middle has a special name. It is called the origin. And its coordinates are 0, 0. So we're going to be talking about points. Points. And points will always have two coordinates. Points always have two coordinates. So that's important. Whenever we say a point, we mean two coordinates, especially if we are talking about the Cartesian coordinate, the two-dimensional. This is called the two-dimensional Cartesian coordinate system. Now, if we have a one dimension just on the number line, so for comparison purposes, if we were just talking about this, and then there's 0, and then 1, 2, 3, so this point is the number 3, then a point has only one coordinate. So this is a one dimension or dimensional space in which we have only one coordinate. So 3 makes sense, just the number 3. But if we are in 2 dimensions, and let's locate the same point, the same relative point, okay. This is not going to be just 3. It is going to be considered incorrect to label this as 3. This should be 3, 0. 3 by itself won't make sense. That is very important. In fact, that's one kind of question I can ask in a multiple choice problem. You know, for instance, we're going to be talking about x-intercepts and y-intercepts. And by that, we mean intersect points. And so a tricky question could be to ask, well, is it 3 or 3, 0? So please keep in mind, if we are asking for a point, make sure it has two coordinates. One number is not sufficient in the two-dimensional Cartesian coordinate system. There is one-dimensional, there's two-dimensional, there's three-dimensional, there is four-dimensional, there's many-dimensional. There's different kinds of spaces we can talk about. Most of the time we are in 1, 2, or 3 dimensions, but we could have more dimensions than that. All right. So again, make sure you go over that. Make sure you review. I know it's easy to get things confused, and I don't mean to be condescending when I say, remember, this line is labeled as horizontal. So some of us, and this one is vertical, and you're thinking, oh, gee, he's teaching us, 1 + 1 = 2. No. I just want to make sure. It's not a condescending thing to remind us what horizontal and vertical thing is in classes. I don't know everybody's background, and it could be that we are just absent-minded, and we just forget. Okay, I know one is, one is up and down, other one is, left and right, but I forget which one is which. Well, make sure you know those, please. That is very, very important. To know the names that are attached to those kinds of lines. So when we have a line, sometimes when I free draw this, the lines are not straight. Please pretend that they are straight. So when we have a line, say this one, okay, and we're typically going to put arrows indicating that the lines keep going on forever. The lines are going to cross the axis. The places where they cross are labeled as, or are named as, this one is called the y-intercept. So this one is, and I'm going to give it a point just for practice. So let's pretend that is 0, 3. Okay, so it just means directly above the origin. That's what 0, 3 means. 0, -3 would be directly below the origin. Okay, so that is the y-intercept of this line. The x-intercept, and again, do not just say 3, please, especially because we're going to be, especially if we ask for the y-intercept point. That's the main key to remember. We're going to, in tests and assessments, I'm probably going to ask for the y-intercept point and make sure it is 0, 3, not just 3. I would, it's easy for me to make up a multiple choice question where one of the answers is going to be 0, 3, the other answer is going to be 3, and you're going to be thinking, oh, well, they're kind of both right. Well, the key is point. Make sure we know that we're talking about a point. And this one, I'm going to make this up. So if this is 3, let's pretend that is 5 on the left. So that would be -5, comma, 0. Yeah. So -5 units to the left, and then 0 units. If this had a grid, and we could clearly see the units, then we would be able to tell, there would be 5 marks. This would be the 5th mark, by the way, and that would be the 3rd mark. So when we have a grid, I just want to show you something. Again, I don't want to take things, like this one. This is not a grid itself, but it kind of shows the marks of the units. What we're counting is the actual mark. So this is 1, 2, 3. Okay, we're not. Sometimes when we count, it is confusing whether we should count the marks or the spaces. We're counting the marks. So this is 1 mark, 2 marks to the right of the origin. So this is the 0th, and then 1, 2, 3. Again, it's better to keep things very, very clear than not clear. So that's the way we draw a line. Lines are have 2 intercepts. Well, actually, I take that back. If the line crosses the origin, then it will, and it is not vertical or horizontal. So before I continue, let me classify lines into 3 categories, actually 4 categories. Okay, so 4 kinds of lines. Yeah, so we're studying lines and we want to understand lines. Just like if you were studying biology, botany, and you want to understand trees, we want to classify trees by different kinds of trees. There's trees that are, see, I'm beginning to talk about things I don't know enough about. So, but I'm sure botanists do classify trees into perhaps, okay, the way they reproduce. That would be one way. Some of them have a fruit. See, again, I'm beginning to talk about things I don't know too much about, so I better stop. But when you study anything, you start classifying. And the reason for that is because we want to understand the objects that we are studying, and we want to differentiate them and notice differences among them, and so that we can also talk about them. So lines, we're going to have 4. A vertical line is one kind of line. So that's vertical. And that's not going to be the same as horizontal. There's a big difference between horizontal and vertical. And then we have oblique, which are neither one of those two, but there are 2 kinds of oblique lines. We're going to label this as a line that goes up, and this one as a line that goes down. And you may be thinking, wait a minute, it depends on the perspective, because, excuse me, if this one goes up, well, it goes down the other way. So it's both, and this one goes up this way and down this way. So how can we say that this one goes up and this one goes down? And I can tell you why or how. We're going to be reading lines from left to right. So pretend we slide this pencil across from left to right. It has to be from left to right. Otherwise, there's going to be, again, two different directions. But if we slide the pencil from left to right, and with the pen, I want to keep up with the line, notice how I have to move my pen upward. See, if again, I'm sliding this pencil from left to right, and in order to keep up with the line, I have to go up. If I continue with this line, and I slide slide the pencil to the right, in order to keep up with the line, I have to move the pen down. So that's how we can tell something is going up or down when we are looking at graphs. Pretend you have, and it doesn't have to be a pencil, it could be a ruler, it could be any vertical object, you know. And if we start sliding up, sliding from left to right, then the pen is going to go up. And then some of you may say, wait a minute, but what if you go from right to left? Then it's going down. Sure, but our default direction is going to be from left to right. So yeah, so the default direction is from left to right. So this one is going up, this one is going down, this one is really not going up because there's no left and right. There's no from left to right. So this one is just called vertical. And this one is called, of course, horizontal. Okay, up, down, horizontal, vertical line. Okay, so those are the basic things. Oh, if a line goes right through the origin, okay, and it doesn't have to go at 45-degree angle, it can go at any angle. I just happen to go approximately at 45-degree angle. Then this point, so the line goes through the origin, 0, 0 is both the x-intercept point and the y-intercept point. It is both of them. In the previous picture here, this line has two different intercepts. This is the y-intercept and the x-intercept. I didn't mention what it was. This is the x-intercept. I did mention it, but I did not write it down. X-intercept point. And this guy is the x-intercept point and the y-intercept point. So if I was going to ask you, okay, what is the x-intercept point? And the answer is 0, 0. What is the y-intercept point? The answer is, again, 0, 0. Okay, so I'm starting to think of the kind of questions I could ask you in assessments. So again, the x-intercept is 0, 0, and the y-intercept is also 0, 0. In order to draw a line, we always need two different points to draw a line. So we need 2 points to draw a line. Or actually, there's another way to go about it, or 1 point, oops, 1 point, there should be a space in between, point, and a direction. Yeah, it's easier to draw the direction from the 2 points, but if I say, okay, keep this direction, this inclination, this particular, and then start the line here, at this point. So then you just move this, make sure you don't tilt it up or down, just keep it this way, and then there's your line. Well, it's supposed to go through the point. I'm going to move the point there. Okay, so that's what I mean. You can have a direction. So I just say this is the direction. It's just harder to tell you, okay, this is the direction, because then, if you carry the pencil with you, you can say, okay, I got to keep it this way, and then it's too easy to move it. It's easier to say, okay, just go so many units to the right, so many units up, and then another point, and then we're all set. The 2 points don't have to be the origin. The 2 points could be somewhere else. In fact, back here, I could give you a point there and a point there, and those 2 points are sufficient to draw the line. Oftentimes, it is good to have the intercepts to draw the line. we're going to do more videos about this line. There's going to be a few videos where we're going to do more things with lines. But next, let's talk about distance. We're still talking about the coordinate system. So distance between points. Okay, so first, we're going to fix one of the points at the origin. Okay, so I guess we're going to do some examples. Example 1. Okay, so what is the distance between the origin and, say, the point 3, 2? So the question is, what is the straight distance? And of course, it is more than 3, because to get to here, we go 1, 2, 3, pretend those are the same length, and then 1, 2. Okay, so again, this is what we are trying to measure, the distance. And well, it's not too hard since we know geometry. This is, if we draw this line down and this across up to this point, then we have a right triangle because this is vertical and this is horizontal. And the angle between vertical and horizontal is 90 degrees. So we can use Pythagoras. This is, of course, 3. This is 2. And Pythagoras says that D, I'm going to try to do this in one shot. And usually we have D squared equals 3 squared plus 2 squared. But I'm going to square root it at once. This has to be a positive number, so there's no need for plus or minus. And then we have 3 squared plus 2 squared. And that's going to be, of course, 9 plus 4, which is the square root of 13. So this is exactly, positively, the square root of 13. Now, I just want to have an idea of how much that is. 13 square rooted, and that is about 3.7. No, 3.6. Okay, so that's about 3.6. Don't write down the 3.6. I just want to have an idea of how much it is. It is more than 3, remember. Not quite 4, 3.6. It's longer than 3. It has to be because it is the diagonal and this is horizontal. So this is longer, not super duper longer, but it is longer. Let's do another example. What if the point was -3, 2? So -3, 2. So this point would be -3, 2. So it's essentially the same triangle, except that it goes to the left instead of going to the right. We're still measuring the hypotenuse, the diagonal. It only makes sense that the answer has to be the same because the triangle is very much the same. We're essentially just flipping the triangle to the other side of the coordinate system. So the answer has to be the same. Now, that makes sense because this -3, so the distance in this case, technically speaking, is the quantity -3 squared plus 2 squared. When we square the -3, that is still going to give us 9. So that is the square root of 9 plus 4, which is the square root of 13. Yeah, that's the key. Regardless of whether this number is positive or negative, we're going to end up with the same positive square. Yeah. Example 3, if we have the triangle going down this way, that would be 3, -2. So this point down here would be 3 to the right, 2 down, 3, -2. If we want to know this distance, D, from here to here, well, we squared the 3, we squared the -2. Well, first of all, does it make sense that the answer is still square root of 13? Yeah, because it is the same triangle as this one. I'm drawing it a little smaller, but because I kind of want to fit all the triangles that I'm going to do in this page. But as we can tell, it is the same triangle just flipped over the x-axis, and then it looks like this. If all we're doing is flipping the triangle over the x-axis, and it is the same because we're going 3 to the right and 2 up, as opposed to 3 to the right and 2 down. So it is the same triangle, just flipped. It only makes sense that the hypotenuse have to be the same. So the answer is going to be square root of 13. We know that in advance because that's what makes sense. And what happens is that we are doing 3 squared plus quantity -2 squared. So keep that in mind. We're always doing the quantity squared. If we end up after squaring with a negative number, something is wrong. Yeah, we always keep adding more to this this has to be positive, this square has to end up, end up being positive. So we keep adding things and we don't subtract ever when we are finding distances. So inside the root, that's what I meant. So this is again 9 plus 4, which is, no surprise, square root of 13. And of course, you know what I'm going to do next. I might just as well finish this. So this point would be -3, -2. Yep. And the distance, it is not going to be a surprise, but let's see how this is written technically. -3 quantity squared plus -2 squared. So squaring the quantity -3 is going to be 9 plus 4, which is going to give us square root of 13, which is about 3.6. Now, don't put down the decimal. We want exact answers many times in algebra. In chemistry, other places, yes, they do talk about significant digits, and we want to end up with decimals and so forth. And it does make sense. I'm not saying one thing is above the other or better than the other. It is just different. The disciplines call for different kinds of writing the answer. Okay. So we know how to handle points, the distance from the origin to any point. Oh, one more quick thing. Example 6. No. 5. Say we want to find the distance from the origin to that point, and let's say this point is 3, 0. Well, the distance is going to be, of course, 3. That's very straightforward. It's almost too easy. And the formula still holds. The formula of squaring this guy and squaring that guy holds. So the distance would be the square root of 3 squared plus 0 squared. So we always add something positive or nothing. That's the worst case scenario. We add nothing. We don't contribute. So by this this point of moving up or down, we're not adding to the length of the diagonal. So this is a weird triangle. I know this is not a triangle, it's just a segment, but pretend you got this triangle here. And if we make this leg shorter and shorter and shorter, then we end up just with a flat triangle. And that would be just this one. I know it's kind of weird, but sometimes we think that way. So this is the square root of 9, which is, of course, 3. Bear in mind that if the point is on the left, say -3, 0, the same thing will happen. The distance would be square root of quantity -3. So we always put the quantity -3, and then we square. And because of that, we always end up with a positive number, 0. Plus 0 squared, yep. Which doesn't really count because we're adding square root of 9 equals still 3. So even though we started with a negative value for x, we end up with 3, and that would be the distance from here to here. So the distances are always positive. We never think about negative distances unless we have relative distances. But if we have just a plain distance, always positive. Okay, so what about points that are not on the origin? Say we start with 3, 2, and then we have another point farther out. Let's put it maybe down here. And so if this is 3, let's label this as 7. 7, 3. This 3 has nothing to do with that 3. I just figure, well, this is 2. I don't want to go another 2, so let's go up 1 more. So we want to know this distance, nothing to do with the origin. So now we got 2 points floating on the coordinate system, an XY coordinate system, and we want to know this distance. There's 2 ways, two thoughts about this. We can move this segment to here, to the origin. We can move it to the origin by subtracting from those coordinates. So that is a shift. That is called a shift. Yeah, so we are gonna shift to the origin. Yeah, this picture So I'm just going to move this here. I'm just going to keep about the same slope. So I'm eyeballing it. Oh, my slope is not quite as good. Yeah. So this is the line. Sorry I'm using pen and it's hard to erase the pen. There. Okay. Yeah. Let's just scratch that. Let's do another picture. So move this here, but I'm going to try to keep the same slope. There we go. Anyway, so move this here to the origin. I'm drawing two pictures. So the 7 has to be reduced by 3. So 7 minus 3, 4. 3 minus 2, 1. And now we know how to handle this. So by subtracting 1 point from the other point, and what we mean by that, coordinate by coordinate, 7 minus 3 and 3 minus 2, we end up with this. This is actually vectors. Believe it or not, we are doing vectors. By subtracting the coordinates one by one, we end up with a new segment, which is exactly the same as this one, except that it is being anchored at the origin. It is exactly the same. And now we have the same problem as example 1. The distance is going to be the same distance, and it will be the square root of, sometimes I skip the step of putting down 4 squared and 1 squared. So bear that in mind. Oftentimes, I'm just going to go directly to 16 plus 1 there. And that's going to be the square root of 17. That is our exact answer. That is the distance between those 2 points, between 3, 2 and 7, 3. Things get more complicated, not a lot more complicated, if the points are not both on the same quadrant. Example 8. So let's say one of the points is, and even if they're in the same quadrant, if the points are, if there is some negative numbers, then things get a little more complicated. So let's say we have, let's continue with a line like this. Let's say this is 4 and negative 4 and 3. And let's say this is, I'm just going to make this up, 2 and let's go up more than 3, just say 6. Okay. So if I want to use the same idea, we want to move this down here, shift it, and we achieve it the same way. So if we want to move to the right, because as we can tell, this segment starts on the left. Yeah, on the left. Yeah, it starts on the left. And so if we want to move it to the right, we need to add this much because we want the segment to line up with the y-axis. So we want to add 4 to negative 4. Yeah. So we're going to end up with this segment, okay? And that's going to be 6. And where does the 6 come from? Start with a 2 and add 4. But think about that. That is really 2 minus negative 4. So we're still subtracting this point. That is interesting. We can subtract this point. And that's going to give us 6. And then 6 minus 3, which makes sense because from here to here, we're going up just 3 units. So this distance is not as, I was trying to do that. This one, my slopes, when I'm transferring, as you can tell, I think the slopes are not quite right. I think this one should be, my drawing is not quite as perfect because the lift, the distance we're going up here, should be just this distance. And I can tell this is higher. So my angle is off here. But pretend it is right, please. So this height should be 3. And where does that come from? It comes from 6 minus 3. So we always subtract the coordinates, always. Yeah. So we really have 6, 3. And then we know how to figure out this distance. It is, so D is the square root of 6 squared, 36, plus 3 squared, 9, square root of 45. But then we have to simplify that. 45 is the same thing as square root of 9 times 5, which is square root of 9, square root of 5. I usually skip this step, but I want to show you. And that is 3 square root of 5. In fact, oftentimes we go from here to here directly because we do those computations in our head. And that's fine. When the numbers are reasonably simple, such as 45, 9 times 5, we can just go from here to here directly. Yeah, so this problem was a little more compounded because we added more things to it. I want to do number 8 again, but differently. So we have this negative 4, 3, 1, 2, 3, 4, 1, 2, 3. And then we're going to go up to 2, 6. I'm going to be a little more precise. 3, 4, 5, 6. So we're about, oops, not that far. That's kind of bumping into the words. So we have this segment of line. A segment, as opposed to a line, is the one that stops, has a starting point and an ending point. A line doesn't stop. I should have probably mentioned that earlier. So there's a difference between segment. I'm going to copy this down. Segment versus line. There's a difference between the two. I'm going to address it in a moment. Okay, so it's the same problem. Somebody could say, wait a minute, can we shift it? So this is the origin. So instead of anchoring the point here, we anchor this point there. So our line is going to actually could go there instead. So instead of shifting the line here, we could shift the line the other way. Can we do that? And the answer is absolutely yes. You just got to subtract the other number. So negative 4, I forgot what this point was 2, 6. Negative 4 minus 2 is negative 6. 3 minus 6 is negative 3. So can we do that? Yeah. We're always subtracting one point from the other, coordinate by coordinate. That's what it boils down to. So the distance is, in this case, the square root of negative 6 squared. Now, don't get fooled by the negative 6, by the negative of the 6. We're going to square, which means we're going to end up with 36 no matter what, plus negative 3 squared. Again, don't get fooled by the negative. That is, when we square, we end up with 9. There's one time when we don't end up with 9, well, not when we're finding the distance. When we are finding the distance, we always end up with 0 or positive numbers, no negative numbers. But in algebra, if we had the negative outside of the squaring, then that would be the case when we don't have a positive number or 0. Anyway, this is the square root of 45. And as we have mentioned above, we simplify that as 3 times square root of 5. All right, so that is the distance. The general formula is this. And you're going to see this in books. Many textbooks will have it. So x1 minus x2 quantity squared plus y1 minus y2 quantity squared. Or the other way around, because this is anchoring one way. I think this is this way, depending on which one. So if this is x1 and y1, and that is x2 and y2, anchoring this way gives us this formula, but anchoring this other way give us the other formula, which is their equivalent, x2 minus x1 squared plus y2 minus y1 squared. So I'm just writing down the general formula. You see them everywhere um, in many, many textbooks. Segment versus line. So let me just differentiate the two. A segment has a starting point and an ending point. Which way it sets, whether it is at this angle or this angle or this angle, it doesn't matter. We have a segment. A line goes on forever. So that is the difference between a segment and a line. The line goes in both. So when we say line, we mean infinite line. Even though we don't actually say infinite, we mean infinite line. So that's a line versus a segment. We gotta be very, very specific. Again, pretend we're studying biology, and the cell reproduction occurs in different ways, and you have to know the names of the different ways of reproduction of cells. Again, I'm just trying to remember things from, middle school and stuff like that. And I remember studying the different classifications of cell reproduction. If you ask me, I don't know them anymore. I used to know them. But the same thing happens here. We're classifying the mathematical objects we're working on. So this one is a segment, this is a line. And you can ask, wait a minute, what if it has a starting point, but it doesn't end? Whoa, so it's a combination of those two. That's called a ray. So we have segment, line, and ray. One word for each one of those objects. So these are geometric objects. Oh, midpoint. Let's talk about, no. Before we do midpoint, let's do an example, an interesting example. I think this is an interesting example. Let's see. Let's say you have the point 2, 7. I'm not necessarily going to draw the coordinate system. I'm just going to draw the point 2, 7 somewhere in space in the plane. And then we have another point here, say, fairly far away, but not too far away. Let's say 10. Oops. 10, comma, comma, and let's pretend we didn't know that number. Let's pretend something was blocking that. And so pretend there's a number behind that. There's no number, but pretend there was a number there. Man, I don't know what that number is. And we want to find that number, but they gave us the distance. Let's say the distance is 9. The question is, what is the number behind? What is that number? Can we find that number? And the answer is yes. Yes, we can find the number. Isn't that a cool problem? You have some information, we're missing information, but we have enough information to figure out what that number is. Actually, there's more than one solution as I think of this, because the line could be going down this way. Yeah, 10 just tells us that this point is to the right of 2, 7. But we don't know whether the point would be up here and up here or down here. So if we have this problem, mathematically there would be 2 solutions. Let's investigate. Okay, so let's call it y, and that's the analytical method. Let's assume there's a solution and then draw information using algebra about that assumption. So let's assume there is an answer to it. So what we know is that 10 minus 2, or the distance, which is 9, should equal the square root of 10 minus 2 squared. 10 minus 2 is 8. Squared is 64. all right, plus y minus 7, oh, y minus 7 squared. Okay, so we cannot actually figure this out because we do not know the number, but we are locking the y, we're clamping the y into an equation or with an equation, so we can figure out what the y is. I don't know about you, but that is very, very exciting. Okay, so square both sides. I wouldn't FOIL that out yet because we're solving for y, and there's a single y here. Um, you will see why it is actually fruitful not to solve, not to FOIL here. So square both sides. So we have 81 equals 64 plus quantity y minus 7 squared. Okay, subtract the 64 from both sides of the equation. So 11 minus 4, 7. 7 minus 6, 1. So we have that y minus 7 squared is 17. Now let's take the square root on both sides. If we're solving an equation and we're taking the square root on both sides, invariably, we have two possibilities. Y minus 7 could be square root of 17 or minus square root of 17. Add the 7. So I'm going to continue here. So y would have to be 7 plus or minus the square root of 17. So there are actually two possibilities. We can have a line going this way, or we could have a line going down this way with the same distance, and both of them having 10 on the first coordinate. However, if you're given a picture like this one, if you're given a picture, then the picture tells us more information. This point, based on the picture, is above 7, because we measure distances vertically, positively going up. So this number has to be more than 7. And the only way to get more than 7 using this y is if we add, not if we subtract. Yeah. So based on the picture, we add to obtain y equals 7 plus the square root of 17. So that is the second coordinate. That would be 7 plus the square root of 17. I know it's kind of awkward to have because it's not a nice number such as 14 or something like that. It's just the way it's written is just awkward. But it is what it is. That's the number. So again, it is important to note that we are using the picture. Let me do 9B. Let's label this as 9A. Just very quickly, I'm not going to redo the whole thing, but if the picture was this picture instead, and we had 2, 7, and 10 blank, let's pretend somebody blocked that and we don't know what it is, and this is still, the distance is 9. What is this? Okay, so based on this picture and based on problem 9A, y, the y that is missing, or the point that we have in here should be 7 minus the square root of 17, because the picture shows that this number is below that one. So instead of adding, we would have to subtract. I think this is a very, very neat problem. In fact, I'm going to consider putting it in the test or the quiz or the assessment, whatever, to figure out what is the other number. And it doesn't have to be y, it could be x. I could give you y, and then you have to figure out x. So I think this is a very, very cool problem. We're going to talk about midpoint now. Given two points, So let's label this as an example 10. That's easier to say 3, 7, and then how about 13, 17? Boy, that doesn't take too much creativity. I guess I'm not too creative because I just added 10 to both of them. So pretend they are random numbers, though. I was just being not very creative and just coming up with 13 and 17 because they're bigger. And by the way, the slope is incorrect because if we are adding 10 and 10, this would be more squarish than this. So this the angle relative to the horizontal is incorrect. But let's stay with that picture. Okay. We do know it is going up, but the angle should be it will be 45 degrees. Because if we go 10 this way and 10 that way, we would, you know what, I can't live with that. I have to draw a nicer picture. So 3, 7, and then if we go 10 and 10, we're going to have 13, 17. So I could have either changed the numbers to make the picture a little more accurate, or just draw the picture a little better. There we go. So that's a little better. That's still not 45 degrees. I can see it's less than that relative to the horizontal, but still is a better picture. Now, we're not going to find the distance. We want to find the precise point that is in between, which we will call the midpoint. All right. Remember how to find the average of two. Yeah, so this is the basic. There's many kinds of averages. There's the weighted average, which we should consider. We don't necessarily have to average everything the same way with the same weight. Some things may be more important, so we want to put more value. So let me talk about averages for a moment. So the average of two numbers, as you probably remember, but let's recall, is the average between two numbers is the sum of the two numbers divided by 2. And that is the regular average. By the way, this is the same thing as half A plus half B. So we're giving to each one of those the same value, half and half. And those values have to, or the same percentages. That's the other way to put it. 50% A plus 50% B. That is the normal standard. I wouldn't call it normal. I would call it standard average. So the standard average gives the same percentage. Now, if you have 3, then you got to give a third value to each one of the elements. If you had 4, then a fourth, and so forth. But you have to give the same weight to all of the inputs. Now, in contrast, we have weighted averages, which don't give the same value. Well, they could, but many times they don't. So for instance, an example could be, what about 20% A and 75% B? So this is given more value to B than to A. It is more important, B is more important than A. So just be aware of the different kinds of averages. It's really cool to talk about averages. Anyway, going back to this point is the average between those two. So that's pretty straightforward. 13 and 3, 16, divide that by 2, 8. 7 and 17, 24. Divide that by 2, 12. So let me just say that again. 3 plus 13 is 16. So I'm doing this formula, A plus B over 2. I'm just not going to write it down because the numbers are very, very straightforward. 3 plus 13, 16. Divided by 2, 8. 7 plus 17, 24. Divide that by 2, 12. There's the midpoint. If you have negative numbers, you still add them, including the negative part of the numbers, and voila, you still end up with the same thing. You just gotta watch those negatives because they can be a little tricky, but just practice them. Let's do a really cool problem though. 11. Let's say we start with 3, 7. We're gonna get to a point. 9, 9, 11. So this is a different problem. And then the line continues. And we do not know what this point is. Something is blocking it. We can't tell what it is. But what we do know is that this is the midpoint. So we don't know where the other end of this segment is. This is the midpoint, but we don't know the other end of the segment. Whoa. How do we do that? Okay. Isn't that cool? I mean, this is like a twisted problem. I mean, I really like when, we're going along and thinking, okay, we understand this, the average, sure, no problem. But then they pull the carpet from underneath and, whoa, now they give us the average. What is the other point, the other end point? Okay, so we got to think this through. Something to notice when you have a midpoint is that whatever horizontal distance you go from here to the midpoint, it is going to be the same thing as going to the other end. So from 3 to 8, we go 5. From 8 to 13, well, we go 5. And the same thing happens in the vertical direction. So this is not the x-axis or the y-axis. I'm just drawing lines to notice. From 7 to 12, we go up by 5. Oh, this was a nice, yeah. And then that was just coincidental that it was 5 everywhere around. The reason for that, remember, is because I was not very creative. So I just said 13 and 17. I just added 10 to each one and 5. Yeah, so something to notice is that whatever distance goes here, the same thing goes the other as we continue, because this is the midpoint. And the same thing happens with the y's. Well, let's use exactly the same logic. From 3 to 9, we added 6, and this is the midpoint. Well, it only makes sense that from 9 to whatever this is, we're going to add 6 again. So 9 plus 6 is 15. So we're adding 15. I mean, we're not adding 15. We are getting 15 from adding 6 from 9. 3, 9, 15. There's a nice sequence. Now, don't add 6 and 6, just like we did 5, 5, 5 all the way around. That changed. And that's one of the nuances that we have to get good at when we are studying mathematics. We're going to change things around. And so we cannot preserve the same numbers. That's one of the ideas behind mixing liquids. We got to change the percentages. And so then you got to keep track of where the numbers came from. Anyway, so from 7 to 11, we went 4. So we got to think how far we went. From 11 to whatever this number, of course, we have to go the same distance because this is the midpoint. So 11 plus 4, 15. That was purely coincidental. I wasn't expecting that. 15, 15. But that is the number, that was the point that I was missing. Now, if you ask a tutor, they'll say, well, use the formulas, use the average formulas. For instance, 3 plus x over 2 should give us 9. So if we multiply this equation by 2, comma, we get 3 plus x equals 18. And then if we subtract 3, then x equals 15. So that's how we get the first one. Some tutors will tell you, why don't you just do the formula? The average of 3 and x, assuming that we didn't know that, so we label it as x, the average between 3 and x is 9, so just set it up as the average equals 9, and then from that, figure out what x is. Does it work? It works beautifully. I just personally prefer to watch what's going on as opposed to just putting this. Now, sometimes I do everything algebraically. sometimes I do things geometrically. So it's not necessarily that this is always better than this. I think a mix of the two is good. Variety, variation. And then, so this is one way to solve the equation. I want to keep it on the same page, so I'm going to squeeze the other solution. So 7 plus y, let's pretend we didn't know what that was. 7 plus y divided by 2 equals 11. Multiply both sides by 2. 7 plus y equals 22. Subtract the 7 from both sides of the equation, y equals 15. And that's how we obtain this other 15. Okay, so can we do this algebraically? Yes, absolutely. For sure. No problem. Can we do this geometrically? Yes, I actually, in this particular problem, I prefer geometric, but it's up to you. You don't have to go one or the other. It's good to see both. Okay, so I'm going to end this video with a little challenge for you. So pretend this point is 7, 11. This point is so farther. Let's be 13, but we don't know what the other is. And here, I don't know if this is even possible because I'm making this up as I go. So 7, 13, 11, we want something that is lower than 11. Let's just say 5. So we're missing two numbers. This number, the x value on this endpoint, and the y value of the other endpoint, we have the midpoint. Do we have enough information to figure those two out? And yes, we do. We do. So I'm not gonna do this. I'm gonna leave you hanging, but you are gonna be able to figure this out, aren't you? So yeah, you are. All right, we're gonna stop the video here.